Welcome to Wildcat Science with Mrs. Haugo. This is Chemistry, Chapter 12, Chemical Equilibrium and Reaction Rates, and today we're starting the second section, Chemical Equilibrium. So equilibrium is a dynamic condition in which the rate of forward process is equal to the rate of the reverse process. And let's highlight a couple of things here. The dynamic means that it's not just a stagnant state. There are things that are happening. So there is a forward process, but it's equal to the reverse process, so we don't see that it changes a lot in the overall picture, but it is changing. So equilibrium, a dynamic condition in which the rate of the forward process is equal to the rate of the reverse process. And a system, and remember we talk about like the system and the surroundings, so the system could be like a beaker of chemicals. The system in equilibrium is not unchanging, it's just balanced. So we were talking about that just before. So let's look at an example. Molecules in beaker A and B are being transferred, but the amount stays constant. So let's say there are molecules in beaker A and molecules in beaker B, and they get transferred between each other, but the same amount is constant. So looking at beaker A, we take some colored water or molecules out of beaker A, and we do the same for B, and then we switch them so that A molecules go into beaker B and B molecules go into beaker A, and we have the same amount. So it looks like it's the same, but it hasn't been unchanged. There have been subtractions and additions. It's just that the subtraction and additions equal each other. So let's look on our books on page 381. And then looking here, same thing. If we were to do that again, we would have equal amounts transferred, and it looks like the amount has stayed the same. So the molecules are being transferred, but the amount stays the same, so that system is in equilibrium. Let's look at another example. Cars in and out of the city. Please write that down, and then let's take a look at it. So looking in our book, we see a picture of a bridge and traffic going into the city and traffic coming out. So let's say there are 1 million people in the city and 1,000 cars go in. Let's just say 1,000 people go in those 1,000 cars, and then 1,000 cars and 1,000 people come out. So there's still 1 million people in the city, but they aren't the exact same 1 million. There has been some going in, some going out, and so the city is in the city population, but it's not unchanged. Hopefully that idea of equilibrium makes sense, and if we get a little bit further into it and some of the details are confusing, just come back to this idea that the system is not unchanging, it's just the forward and reverse reactions are balanced. So there are two types of equilibrium, physical equilibrium and chemical equilibrium. And chemical equilibrium would involve chemical reactions, and physical equilibrium would involve physical changes. So in a physical equilibrium, the system is balanced between physical changes, and one example are phase changes of water. So please take a minute and make this drawing. So what do we have here? So we have a beaker, and you can probably make a nicer beaker than mine, and it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 molecules of water in the liquid phase, and that's the initial state of the system. And then some time passes, and we see that some of the water evaporates. So now we have 3 molecules in the gas phase and 7 molecules in the liquid phase. And eventually the system, the beaker with water, will reach equilibrium. so that whenever the rate at which the liquid molecule is going into the gas phase is equal to the rate at which the gas molecules are going back into the liquid phase. So in this example, we always have 3 molecules in the gas phase and 7 molecules in the liquid phase, but it's not always the same exact molecules. And let's take a look, before we jump into chemical equilibrium, let's take a look in our book. This is the same concept, just a little bit prettier. We have all of our molecules in the liquid phase, and then day 2 we see some molecules have evaporated. And then when it's in equilibrium, the rate at which the water molecules in the liquid phase evaporate and then is balanced with the rate at which molecules will condense back into the liquid phase. They condense on the glass and then fall down and become liquid again. That was the physical equilibrium, and let's talk about chemical equilibrium, which is the balance between the forward reaction and the reverse reaction in a chemical reaction. So in chemical equilibrium, the concentration of the reactants and the concentration of the products stays constant. It's not the exact same molecules, but the concentration is the same. So it's dynamic, but not unchanging. So in a closed system, if you remember, a closed system is one where the system isn't interacting with the environment. It does not mean that the amount of reactants equals the amount of products. So this is a common misconception, that it'll be like, oh, well, I'm going to have 1 mole of reactants and 1 mole of products. It's not necessarily that. It's just that the concentration of the reactants stays the same. So let's look at an example. We have dinitrogen tetraoxide, which is a gas, and it's in a reversible reaction. I have a double-headed arrow with 2 moles of nitrogen dioxide gas. So looking at this, dinitrogen tetraoxide is a clear gas, and nitrogen dioxide is a reddish-brown poisonous gas. So the reactants and products are very different from each other. And nitrogen dioxide is produced by car exhaust, and it creates smog, which causes health problems like asthma and emphysema. So the equilibrium position, which is the concentration of products and the concentration of reactants, once equilibrium has been reached, has environmental health consequences. Looking back at our equation, if something favors the forward reaction, this is going to have environmental impacts. It's going to have health impacts on people's lungs, and people in certain conditions can die from that. So whereas if it favors the reverse reaction, it's not such a big deal. So the equilibrium position is important. So what can we learn from that? So let's think about what conditions favor the products and what conditions favor the reactants, and we're going to look in our book on page 382 and 383. So here we have an experiment, and we have a little ampule, it looks like, of gas, and here's our equation again. Dinitrogen tetraoxide is in a reversible reaction with nitrogen dioxide. It looks at room temperature like we have some of both. We have some clear and we have some reddish brown molecules of gas in there. And as it cools down, we see that it becomes more clear, both here and then when we cooled it down after heating over here. So that favors the reverse reaction. It favors the reactant. And then when we heat it up, you can see that there is more of the product, nitrogen dioxide. So my question is, does increasing the temperature favor the forward reaction or the reverse reaction? If you said the forward reaction, you would be correct. It favors the products. Let's take a look at this diagram to see what's going on. So if we are to start with only dinitrogen tetraoxide, we see that the concentration of the reactant will decrease and then it will level off. And then the concentration of the product will increase and then it will level off. If we started off with no dinitrogen tetraoxide and all nitrogen dioxide, we can see that the reverse would happen, but the product would be the same. So some of the nitrogen dioxide would form a chemical reaction and form dinitrogen tetraoxide, and then it would level off, and you can see it's at the same level as before. And then some of the dinitrogen tetraoxide would form, and then it would level off, and it would be at the same level as before. And here you can see an example of this in real life. This is the skyline of Los Angeles, and you can see it's smoggy, and it has some of that reddish brown nitrogen dioxide, which is a poisonous gas. So not so good, and that comes from car exhaust. Let's look at a second example. Here we have 2 moles of sulfur dioxide gas reacts with 1 mole of oxygen gas and is in a reversible reaction with 2 moles of sulfur trioxide gas. So we're going to look at some diagrams and figure out which side of the reaction is favored. So if we start with a lot of sulfur dioxide and some oxygen, we can see as time goes by that those reactants will react and form some of the product, sulfur trioxide. But if we started with a different initial condition, when we started with all sulfur trioxide, we can see some of the product would turn back into the reactants. And so some of our reactants would form. And the equilibrium position is the same no matter if we started with all reactants or all products. So in this system, is it the forward reaction or the reverse reaction that is favored? If you said the forward reaction, because we end up with a higher concentration of sulfur trioxide, you would be correct. So we know that some reactions are going to favor the product side and some reactions are going to favor the reactant side. But our question as chemists is, how can we influence a reaction's equilibrium and make more of a product? Well, there are factors that affect the equilibrium. So changing these factors will affect where the equilibrium is, either favoring the forward or the reverse reaction. The concentration, if we increase or decrease the concentration of the reactants or products, it will change the equilibrium. Temperature, if we increase or decrease the temperature, it will affect the equilibrium. Pressure, especially when gas is involved, if we increase or decrease the pressure, that will affect the equilibrium. And volume, if we increase or decrease the volume of the system, that will affect our equilibrium. And these factors bring us to Le Chatelier's principle, which we will discuss next time. All right, see you then. Bye.